Welcome back to module 6. We have presented so far we have given the formal derivation of the quantum adiabatic theory, which assumes that the let's say, taking an example of a particle in one-dimensional box, the box is expanding very slowly, and if the box is expanding very slowly, then at the initial time before the expansion started, if it was in the nth non-degenerate, discrete non-degenerate stationary state, the particle if it was there, then after the expansion the particle will remain in the nth non-degenerate stationary state of Ht, but the wave function accumulate two different phases, and these two phases are the dynamical phase, which has to be included in the wave function. So, the formal statement of quantum adiabatic theorem, we will write down the formal statement of the quantum adiabatic theorem. Under the quantum adiabatic theorem, the Hamiltonian of a quantum system, the Hamiltonian of a quantum system changes very slowly with time, from an initial form which is H0 to a final form Ht, during which this adiabatic process occurs. And as a result, the quantum system which was initially at t equals 0 or before the beginning of the process in the non-degenerate nth eigen state of H0. So, the quantum system which was present in the nth eigenstate of H0 will remain in the non-degenerate nth eigenstate of Ht, because the final Hamiltonian is now Ht. This simply means that the ground state, what does it mean? It means that the ground state system will remain in the ground state, before and after the adiabatic change of the Hamiltonian, without making transition to the excited state. So, ground state will remain in the ground state, but the wave function which was before psi n0, in this case ground state. So, we consider ground state to be if it was psi n0, now the wave function would be psi n t, that is the wave function, but it has now additional phase. The phase is e to the power I gamma nt and e to the power I theta nt. That's the difference. So, a wave function which was staying here, now the wave function is this one after the adiabatic process has is over, immediately after the adiabatic process is over. Here this theta n is called dynamical phase and gamma n is called geometric phase. So, this is the kind of summary of quantum adiabatic theory. The at time t equals 0, it was the wave function of the particle will be represented by psi n 0. At t equals t time, after immediately after that process is turned off, now the wave function would be psi n t, that is the stationary state wave function obtained from h t. But in addition to that wave function, I have now additional phase factor. This phase factor now accumulated due to this adiabatic change, the change of the process. So, the entire pictorial viewpoint is following. Let us assume that I have one box of length L2. So, if I have a box of length L2, I know what is the wave function of that particle. Particle wave function will be given by psi n, which is given by this. It depends on L2 distance. Now, I will consider a box which is starting from an expanding box starting from L0 to L2. This L2, this is the static box, the box is not expanding. But here in this expanding box problem, it is slowly expanding from L0 to L2. Finally, I have achieved this dimension L2, which was present in the static box. So, then in that case, the wave function immediately after the expansion for this expanding box will be this wave function, which is coming from the static box wave function, multiplied by two different phase factors. These two phase factors are coming just due to the dynamical evolution of the box. If it was not dynamically evolving to reach that dimension, we should have this static wave function. The static wave function is given already, the particle in the box. But because it is dynamically evolving, due to that dynamical evolution, the wave function, the static wave function will come and it will be augmented or multiplied by two different phase factor. One phase factor is called dynamical phase factor, another one is called geometric phase factor. These two phase factors will be added to the wave function because of the dynamical evolution, this adiabatic change of the box. So, this is the dynamical viewpoint of the entire theory which we have presented, and the entire derivation is to get this expression, final expression for the wave function, final wave function, and there is no n here. This is actually the state at time, at this time. So, we will go back to our problem of one dimensional problem, and we have seen that the wave function will be represented by this this entire wave function at time t will be represented by this, and now we will explicitly calculate what would be the expression for or values for this dynamical phase and the geometric phase for the given problem. The problem is that a box is expanding from L1 length to L2 length, and this is t equals 0 and this is at time t. It has up to time t it has expanded, and we will say that we will assume that assume that my particle before the expansion it was in the ground state. So the ground state wave function will be written like this way. It would be square root of 2 by L sine pi x by L, and it was ground state, that's why it should be L1. So this was the wave function of the particle before the expansion, but the particle, the box has expanded from L1 to L2, and L1 is the box length less than equals 0 just before the expansion started, and L2 is the length when it has expanded completely, and immediately after the expansion this is the box length L2. So according to adiabatic theory, the wave function at time t immediately after the length has expanded to L2, what is the wave function of the particle? That is represented by psi 1t, that is the ground state wave function at time t, and then its phase factors will be multiplied. So we will explicitly see how to get that. First we will look at this theta 1t, how much is going to be. Theta 1t will depend on this integration that we have seen, and E1, the energy, we know that it is going to be pi h cut square by 2m L, this is t dash square. So any time, so 0 to t, this is the time interval we have, the expansion time interval, at any time is given within this interval is going to be t dash, and that's the integration we have taken. So if this is the expression for the ground state wave function, ground state particle, the energy of the particle is given by this. This is the instantaneous energy of the particle in the ground state. Then we will say that we'll assume that the expansion occurs at constant rate v, that is dl dt is constant. And if dl dt is constant or dl dt dash is constant, then one can write down dt dash equals dl by v. That we can do. And what is L here? L is the instantaneous length. So L has changed from L1 to L2, and any instantaneous length in between is going to be L. So that's the definition of this. So what we can do is that this total time integration can be converted to spatial integration like this way. 1 by h cut this rate of change, and now it is going to be L1 to L2. Then this integration is going to be pi square h cut square divided by 2m L square dl. L is an instantaneous length in the interval L1 to L2. So I have been able to convert this integration to in terms of L, and if we do that, then I'll be able to integrate it very easily. I'll be able to write down as minus pi square h cut by 2m v, this is going to be L1 to L2 1 by L square dl, which is nothing but pi square h cut by 2mv 1 by L, the L1, L2 is pi square h cut divided by 2m V 1 by L2 minus 1 by L1. So we finally get this theta 1 t, this value, that is the dynamical phase, which is accumulated by the wave function due to this dynamical evolution, is going to be pi square h cut by 2m V 1 by L2 minus 1 by L1. So we have got one phase factor for the expanding one-dimensional box problem. Next we look at the geometric phase. In the geometric phase we have this expression, and here psi 1 t dash, psi 1 time dependent because it is the psi 1 L, it is actually depends on L, that's why, and L is time dependent, that's why psi is time dependent. So one can write down this derivative as follows: psi 1 L. Again we are converting this expression in terms of L. So if we do that, then I'll be able to write down I, then this is going to be L1 to L2 integration psi 1 with respect to L, then dl with respect to this we can insert here, and we can convert this one to this. So we know that the psi 1 is nothing but square root of 2 by L sine pi x by L at any instant of length L. So L, we said that this is L1, this is L2. At any instant of time, the length of the box is given by L in between these two interval. So that is given by this. The wave function, ground state wave function, will be given by this. So if I have this ground state wave function like this, then I'll be able to get the derivative with respect to L, because that's derivative what I need here. It's going to be now derivative with respect to L is going to be square root of 2 by L sine pi x by L. This is going to be square root of 2 minus 1 by 2 L to the power minus 3 by 2 sine pi x by L plus square root of 2 by L minus pi x by L square, then cos pi x by L. So we get this first derivative with respect to L of this function, and once we get the first derivative, we will be able to, because I have to multiply now psi 1. So if I want to find out psi 1, this partial derivative, this product will give me 2 by L sine pi x by L multiplied by this entire function. I have to multiply the entire function, which is square root of 2 1 by 2 minus 1 by 2 L to the power minus 3 by 2 sine pi x by L plus square root of 2 by L minus pi x by L square, then cos of pi x by L. So if I multiply, then finally what I get is going to be 1 by L square sine square pi x by L minus 2 pi x by L cube sine pi x by L multiplied by cos pi x by L. These two terms we get, and in the end we have to get the integration. So this psi 1, this integration is nothing but 0 to L psi 1, so this is psi 1 star psi 1 dl dx. Because this ground state wave function is a real function, so psi 1 star and psi 1 are equivalent. They do not have the complex conjugate because they are real. So what I have to do now, this entire thing has to be integrated 0 to L 0 to L, then minus 1 by L square sine square pi x by L. This is one term. Then another term is going to be I put it here, minus here. There is another term. Another term is going to be 2 pi by L cube. And this integration, remember, this is coordinate space integration. So this is over x. So this is going to be dx. That's why we can take out this L square term 0 to L. So we can write down like this way. And then we have 0 to L sine pi x by L and cos pi x by L dx. So this is the integration which we need to perform. So we'll perform it step by step. First we'll look at this integration, this is the first integration. In order to do this first integration, we will use trigonometric identity as cos 2 theta equals 1 minus 2 sine square theta, or minus 2 sine square theta equals cos 2 theta minus 1. We'll use this one because in this part, if you look at this part, which is minus 1 by L square 0 to L sine square pi x by L, we will make it like this way. We'll multiply by 2, and then this is 2, this is dx. So if we do that, then this part can be written as cos 2 theta minus 1. So we can write down this to be cos 2 theta minus 1. So we'll write down cos 2 pi x by L minus 1 dx. If we do that, then I get minus I get 1 by 2 L square by 2 L square 0 to L cos 2 pi x by L minus 1 by 2L square 0 to L dx. So this can be written as 1 by 2L square sine 2 pi x by L divided by 2 pi by L 0 to L minus 1 by 2 L square x 0 to L. Now if x equals L, then this becomes sine 2 pi. Sine 2 pi is going to be 0, and then when sine x equals 0, then also 0. So the entire term goes to 0. What I get finally is minus 1 by 2 L square L, or in other words 1 by minus 1 by 2L. So this term we have neglected this negative term. So this part is giving me minus 1 by 2L. On the other hand, not this part, we have included this negative sign here because this is negative. So this entire part is becoming minus 1 by 2L. The other integration, this integration we have to take a look at it. This integration we have already got, that is minus 1 by 2L. Now we're looking at this integration. In order to do this integration, we will be able to write down 2 sine theta cos theta equals sine 2 theta. So this part can be rewritten as sine 2 theta. So I'll be able to write down 1 by 2 pi by L cube 0 to L see this 2 will be taken inside. This is, I have x, then 2 sine pi x by L cos pi x by L dx. That's the integration I have, which is which can be written as 2 sine theta. So this 2 will be gone, and this is going to be now 2 sine theta dx. And I will now multiply this pi by L cube. I keep it as it is. Then I multiply with this factor L by 2 pi. There is a reason why I am multiplying. Then 0 to L. Then I multiply x. And then I write down minus 2 pi by L. Then sine 2 pi x by L dx. The reason I am doing it, because this part now, this entire part can be written as derivative of cos value. So it is going to be d dx of cos 2 pi x by L. Now I can integrate by parts. Integration by parts, if I do that, then I will be able to write down 1 by 2L square, then x cos 2 pi x by L 0 to L minus 1 by 2L square 0 to L cos 2 pi x by L dx, which is 1 by 2 L square L cos 2 pi minus 0 minus 1 by 2L square sine 2 pi x by L 0 to L multiplied by L by 2 pi. So what we see here is that this entire term would be 0 for the limit we have set. So that part vanishes, and as a result cos 2 pi is 1. So finally I get L by 2L square, which is nothing but 1 by 2L. So this part we have already got minus 1 by 2L, and this part we are getting, the remaining part we are getting as plus 1 by 2L. So finally what we get is that this integration, this value is becomes 0. And if this integration is becoming 0, then gamma 1 at time t is given by 0 to L1 by L to this is the limit, and then this integration psi 1 L then dl, this part becomes also 0. So what we are seeing here is that the geometric phase becomes 0 for an expanding box when the box is expanding from L1 to L2. But it is accumulating dynamical phase, but geometric phase becomes 0. So what we have observed is summarized here. The wave function, initially the wave function was this, finally the wave function would be this multiplied by e to the power I theta n t, theta 1 t, because we started with the ground state wave function, so it is going to be 1 theta 1 t, and gamma vanishes. So this is the final wave function after the expansion, and theta 1 t is given by this expression. When we see this geometric phase to be 0, we can remember that any time if the wave function is real, then the geometric phase after the adiabatic expansion is going to be 0. That's another consequence of adiabatic theorem, which we can prove actually, but will not do it immediately. We have come to the end of this present module. In this module, we have given theories which can be used to solve analytically the TDSE, time dependent Schrodinger equation, to explore the dynamics of a quantum system. We have presented time dependent perturbation theory, where we have which can be used to find out the dynamical evolution of a system. Time dependent perturbation theory will be very frequently used for light absorption, light emission, and non-radiative transition. In addition to this time dependent perturbation theory, there is another analytical approach which is available, which is called quantum adiabatic theory, which we have presented in the light of expanding one-dimensional box. We will end this session and we will meet again in the next module.